Okay. So towards proving spectral theorem, we were talking about the so-called spectral operators. Okay, so we started with the spectral measure. Okay, we started with the spectral measure. P be a spectral measure. Sorry, not this. We have a measure space, which will be usually real line with Borel sigma algebra or complex plane with Borel sigma algebra, whichever. Okay. So omega script F, measurable space. Then we have a spectral measure, all projections in H, and which are additive, and where P of E in F is a collection of projections, is a commuting family of projection. I mean, I didn't say that, but it will follow. Okay, from the countability, additivity, and all, it will follow that it's actually commuting projections. Okay, you can, and also it's also true commuting family, or you can assume if you want commuting family of projections. Family of projection, and it's also true that P of E times P of F equal to P of E intersection F. P of E times P of F is going to be the projection. I mean, they are commuting, so it will be the projection onto the subspace, intersection of the subspace. P of E corresponding to one subspace, P of F corresponding to one subspace. So P of E times P of F, if you multiply to commuting projection, that will be the projection onto the intersection of the subspace. Okay? So that will be P of E intersection F. Similarly, for the sum also you can define, and that will be the space generated by that. So it satisfies these properties. It will all follow if you just use the additivity property. Okay. Then for any F measurable, F from omega to C measurable, we defined first domain, which is all those X in H, such that, so if you have this, then mu xy, mu yx equal to mu x dot is equal to y p of x. This gives a complex measure, and when y equal to x, this will give a finite positive measure. Okay. Integral mod f square d mu xx is finite. So we took this as the domain for the operator T of F. Then T of F is an operator from H to H. I say H to H. I mean, the operator is not defined on H, but we have to have the Hilbert space in the background. So we should always say it's an operator on H. Okay, it's an operator on H with domain of TF equal to DF. Okay? That's how we should write. Not that it's not an operator from DF. Okay? So TF such that it satisfies the following property, such that y TFX is equal to integral over there exists TF, there exists unique TF. This is my notation for unique TF. We proved this. Okay. We proved this. This is equal to integral over omega F d mu x. Okay. Well, this is integration with respect to complex measure, which I mean, it's the same as the any complex measure. Actually, it's a theorem that any complex measure can be written as linear combination. I mean, it's written as mu1 plus I mu2, where mu1 and mu2 are real measures, which are called signed measures also. Okay. And any real measure can be written as some mu plus minus mu minus for some. It will have disjoint support also. So those theorems are there. So it's all well defined. I mean, using the integration with respect to positive measure, you can define all these things. So it's well defined. Okay. And further, we proved that the norm of TF square is equal to, this is something well defined, norm F square d mu xx. Okay. We found that this is equal to this. Now, in the process of proving the proposition, we want to prove one TF star. Of course, this domain is dense. Okay, this is contained in H, which is dense, which also we proved. Okay? That is a dense domain. TF is densely defined operator, so it has an adjoint. And the TF star is nothing but TF bar. So that is the first claim. Okay. The second claim of the proposition is, if you have two measurable function, fg measurable, then domain of TF then domain of course, if you have two unbounded operators, you can multiply them. The domain will be given by all those elements in the domain of G, such that TG, I mean, all those elements in domain of TG, so that when you apply TG, it should be in the domain of TF. I mean, you should be able to make sense of this operator. That's all. Okay. So domain of TF DG is contained in DFG. Okay. Further, it's also true that domain of DFDG is actually equal to DG intersection DFG. Okay. This is DFG. Okay. So we want to prove these two things. Okay. Okay. And the proof is, I mean, we will use something about spectral theorem for bounded operators, which we have already used. Okay. We have already used when we proved these things. So do you remember how we were struck in proving that norm equality? I mean, how we did, we have this property that if we have f is bounded, I'm just recalling that proof, and then class once again, I want to tell you something.